First, I will talk about the classical situation, meaning no quantum. I will come to the quantum case later. And I'm talking about everlasting security. This is also a topic that we had in this workshop, meaning we assume computational assumptions during the protocol, but we'll let the adversary become unlimited afterwards. And now, in everlasting classical security, the goal we would like to show is that every task that can be realized with unconditional security relative to a semi-honest, meaning just curious but not actively cheating, adversary can also be implemented with everlasting security relative to an active adversary using temporary assumptions only during the protocol run. And the idea behind it is relatively simple. We're using unconditionally hiding commitments and zero-knowledge arguments built on the unconditionally hiding commitments to enforce semi-honest behavior. But now we're talking about using some protocol and using unconditionally hiding commitments on top of them. So question we should ask is, how do unconditionally secure commitments behave under composition? And to study composition, there's this universal composability framework, meaning we're not defining security by certain properties, saying, oh, it's hiding and binding, but we define security by comparing a real protocol pi interacting with a real adversary with some idealization, an ideal functionality which is implemented by a trusted authority and run by a trusted authority and cannot be corrupted. If you corrupt a party here in the ideal, you can just change the input or change the output, like not accepting the true output for yourself, but you cannot do anything else. So the adversary here is very, very limited. So this situation is kind of secure by definition, and we would like to have that for every machine, every hostile environment interacting with the real protocol and the real adversary, for this machine it is indistinguishable if it interacts with the real or with this ideal world. Then we say this real protocol implements this ideal functionality. And now this definition has the big advantage that you can now plug this protocol into larger applications and nothing bad will happen, because if the larger application would become insecure, this larger application could have been one possible hostile environment, and we would have found out before it wouldn't have fulfilled this security definition. And now to come from universal composability, from this framework, to everlasting security, we just do one very easy step. The environment machine that becomes unlimited after termination of the protocol. That's all we change in the protocol, in the setup, in the framework. So in the classical case, we interact, we're bounded while we interact, and after finishing of the protocol, after termination of the protocol, the machine becomes an unlimited distinguisher. In the quantum case, it would be the same. We would be like BQP, bounded during the interaction, but we would become unlimited afterwards. And unfortunately, bit commitments are very problematic in this universal composability framework. From scratch, they're impossible. And the reason is, if you can commit in the real protocol, then this simulator must commit to this ideal functionality and must hand the bit in the clear to the ideal functionality. This must be the bit in the clear. However, if this machine commits and just uses the adversary as a relay, the adversary learns as little as the honest receiver. So the bit should be hidden here, but must be extracted there. So you cannot fulfill this from scratch. Same reason is you can unveil here. You must be able, you can commit here and unveil later. You must be able, as a simulator, to commit without knowing the actual value. And later on, you must be able to, in this ideal setting, open to whatever it was. But of course, the real adversary should never be able to open to whatever he wishes. So we have the problem that this model is so strict that we do not have commitments from scratch. All the commitments we were discussing during the workshop would not compose in this way. We need something additionally, like the sun, which is called a common reference string. A common reference string is something like the sun, where you can extract randomness, and in the real model, you cannot lie about this randomness. Whereas in the ideal model, the simulator can make up this randomness. And now, if we assume that the randomness which we take from the sun is interpreted as a public key, then we can commit by encrypting with this public key. This will be hiding in the real world, but here the simulator makes up this public key, and he can make up the public key in a way that he knows the secret key. So now we are able to extract in the ideal model, but we have the hiding property in the real model. Now, people thought, oh, but unconditionally hiding protocols are not possible maybe anymore because we need to extract somehow. Interestingly, unconditionally hiding UC commitments are possible. But for that, the common reference string has to be chosen very differently in the real and in the ideal model. In the real model, it must be chosen in a way that the resulting messages do not contain the bit. It's perfectly hidden. Whereas in the real model, it should contain the bit. You can think of the common reference string, if we stay with this public key idea, as maybe being a lossy trapdoor function here, which is not lossy there, meaning an encoding scheme where nothing's in, if you do it here, but you can extract from it there. But unfortunately, our definition of security was this machine should not be able to distinguish in the long run, after becoming unlimited, between the real and the ideal. But now I said that the public key here is lossy, the public key there is not. This will be distinguishable in the long run. And so, even though we have unconditionally hiding UC commitments, they are not long-term secure. It looks a little bit artificial, but unfortunately that's how the definition is, and we have not yet a much better composability framework. And also one could think of the adversary using the common reference string in the protocol in a way that it actually matters that the common reference string can be distinguished in the real and in the ideal in the long run. So unconditionally hiding UC commitments are possible, but they are not long-term secure. The CRS is chosen in a way that we can distinguish it in the long run if it was lossy or not. Yeah, this even implies that everlasting security is impossible for a large class of setup assumptions, not only the common reference string, but also the PKI model and many other models. And now I would like to introduce a different idea to obtain composability, which is a little bit weaker, but we have no setup assumptions. So we can now be sure that something as artificial as, oh, we distinguish the CRS, we're not even looking at the protocol, we're just distinguishing the CRS, something as artificial as that will not happen here. This concept is called CCA commitments. CCA commitments are commitments which have a tag. And even if I allow the adversary to break the commitment for a specific tag, all other commitments using other tags still remain hiding. Okay? And now, instead of giving some common reference string about which the simulator can lie to the simulator, we give him super polynomial power, but just the right amount of it. Just the amount to extract the commitment here with this tag, but no other commitments in other protocols. And this gives you strong composability guarantees, even though not as strong as the universal composability framework. But I will not discuss this. I will just tell you that CCA commitments are a very good way to obtain composable commitments. But if we look at the CCA commitments in the literature, they are all extracted by super polynomial power, meaning if the commitment can be extracted by an unlimited machine, then the security cannot be everlasting because the information is in there. The unlimited machine just broke the commitment and extracted the value. So this will not be everlasting security. But if we look in the proof of the existence of CCA commitments uses that one can extract the committed value also by rewinding the environment. Rewinding meaning making several copies and running it with different inputs and then combining all the outputs the environment gave, and then we will obtain the value. And now the idea we could have is don't make the simulator computationally unlimited, but give him the ability to rewind the environment. Then the CCA commitment can be unconditionally hiding. We're not extracting by super polynomial power, we're extracting by the rewinding. So this implies a commitment with a limited composability, which offers us everlasting security. So this is the picture. The simulator is able to make copies of the environment and ask different questions, and so extract the value. And due to the construction of CCA commitments, other commitments remain hiding, even if one specific commitment is extracted by rewinding. And so we kind of inherit the composability features of CCA commitments here. Unfortunately, they are interactive. Another idea to obtain everlasting composable unconditionally hiding commitments is to use hardware tokens, like you have to sign the message before you commit to it. But if you have to sign the message by a token, by a signature card, then you have to give it to the signature card in the clear. And this can be a trick to extract the commitment as well. Okay, so either using hardware tokens, which you have to give the bit in the clear as a trick to extract the commitment, or by generalizing CCA commitments to the unconditionally hiding case, we get unconditionally hiding composable commitments in the classical model. But what happens in the quantum case? The promise to make every semi-honest protocol secure against malicious adversaries is a large promise. But the promise in the quantum case is even larger. Given commitments, one can implement oblivious transfer, and I don't need to explain it. Given oblivious transfer, one can implement any secure multi-party computation, meaning any task where we together work on secret data without revealing the data. So the idea could be, using unconditionally hiding commitments to obtain everlasting security for any multi-party computation. Meaning I have computational assumptions only during the quantum protocol, and later on my machine becomes unlimited, and still we have everlasting oblivious transfer. This would be our dream. But how do unconditionally secure commitments behave under composition in a quantum world? Okay, oblivious transfer, I chose a different one, is a trusted erasure channel. This is, of course, equivalent, as you proved. But in this view, Alice just sends a bit, and Bob either receives the bit, 50% probability, or receives some erasure symbol. This is also why it's called oblivious transfer, because the transfer of the bit is kind of oblivious. And now, couldn't we implement this based on the quantum channel? Meaning we have two bases, which cannot both be measured. So we prepare a bit 0 or 1 in the computational or in the diagonal base and send this qubit, and the receiver measures in this or that basis at random. After the measurement, Alice announces the basis used. If they don't match, the measurement results uncorrelated. This is like an erasure symbol. And if they match, Bob received the bit as it is. Yeah, but this is not a secure implementation. Bob could delay the measurement here until Alice announces the basis, and then measure whatever is inside with 100% probability. Dominic Myers and Lowe and Chow proved that oblivious transfer and commitments are impossible with unconditional security. One can basically always delay the measurements. Given commitments, we can force someone to measure. You have to commit to the qubits you prepare, meaning commit to the classical information of how you want to prepare the qubits. And you have to commit to your measurement results. This allows to check on a test set if you actually measured. And now either you get caught or you measure often enough for oblivious transfer to become possible. And now, of course, we would like to have these commitments to be unconditionally hiding. So commitments imply oblivious transfer in the quantum world. How about everlasting security for oblivious transfer? So we proposed this CCA commitments, which are extracted by rewinding. This commitment is unconditionally hiding and completely computed by the adversary. So the adversary doesn't need to measure. He can compute all this in quantum superposition, and then he can still delay all measurements. So this cannot be a good solution. But kind of, I told you it has very good composability properties. What's going on here? This does not imply everlasting security for OT. So do those commitments really compose, as I told you? Yes and no. Classically, they do compose, but not in the quantum world. Rewinding is a completely classical concept. You make copies. Yeah, quantumly, this would require cloning, which is impossible. So the proof using rewinding does just not hold for quantum machines. For hardware tokens, it is possible. The value of the commitment is first given to the token, for example, to be signed. The token accepts only classical input, hence the value has been measured and a delay of measurements is not possible anymore. So this implies everlasting security for OT, but you need to trust the token to be tamper-proof. Could we achieve everlasting security with less trust? And here I would propose to use decoherence. Decoherence means we can store maybe a large amount, not bounded storage, maybe we can store not a large amount, we can store a large amount, but not for an arbitrary time. So the quantum information will decay. The goal would be, given commitments, one can implement OT. Given OT, one can implement any secure multi-party computation. And now using unconditionally hiding commitments and the decay of quantum information, we would like to have everlasting security for all multi-party computations. But what is the appropriate model? Here I would say we have an environment machine which is quantum polynomially bounded, can do any attack, anything, but is polynomially bounded. But then it can even simulate how the quantum states decay. But then it has to output a lot of classical information to an unlimited distinguisher, meaning my adversary becomes unlimited after all quantum information is decayed. And now I conjecture, in this model, everlasting security can be achieved from unconditionally hiding commitments. Thank you.